Welcome. Today we're going to do some more examples. In particular, I want to answer some questions about, solve some problems regarding minimal polynomials, degrees and factorizations of polynomials into irreducibles using some of the knowledge we gained recently. So the first problem I want us to look at is trying to find the minimal polynomial of radical minus 3 plus radical 7 over q. We've looked at these kinds of problems, so how do you find a minimal polynomial? Well, you first find a polynomial that has this number as a root, and then try to show that it's the smallest possible degree. So let's find a polynomial. You already know methods of doing that. So I would first try to square this number. Which gives me minus 3 plus 7 plus 2 radical minus 21, which is 4 plus 2 radical minus 21. If I subtract 4, I get 2 radical minus 21, and if I square both sides, I get 4 times minus 21, so minus 84. Adding it to this side, I get 0. So as a conclusion, this number is a root of x squared minus 4 squared plus 84, which if I write it out is the same as x to the 4th minus 8x squared plus 16 plus 84 x to the 4th minus 8x squared plus 100. If I could show that this polynomial is irreducible over q, then I would know this is a minimal polynomial. But how would I do this? Well, I could try to use the Eisenstein criterion, but unfortunately the primes that divide all the coefficients, there's only one prime, namely 2, that divides all of them, and 2 squared also divides 100, so I cannot use the Eisenstein criterion. Okay, and it's a degree 4 polynomial. So how do I know it's minimal? How do I know that this doesn't satisfy anything of lower degree? Is of smallest possible degree. Well, if you try to just approach it directly from the definition, you would now have to try to show that this number doesn't satisfy a quadratic and a cubic polynomial. But we can use some of the knowledge we've learned in the recent videos to address this. So what can I do here? So I'm going to erase this, and I'm going to look at field extensions. So I have the following diagram of fields. And the first thing is, what do I know about this degree? I know that this degree is now less than or equal to 4 because I found a polynomial of degree 4 that this element satisfies. So how do I know that this is exactly 4? You see, the first thing I want to try to do is I want to show, so let's show that radical 7 lies in this field. Okay, let's first show it, and then after I do it, it might become evident why I did it. How would I show that? So what do I need to show? So i.e. that we can write radical 7 as a0 plus a1 radical minus 3 plus radical 7, and then its square, and then its cube. Okay, for some a0, a1, a2, and a3 in cube. I know I don't need any more terms than going up to the cube, because I already know that the degree of this extension is at most 4. Maybe I need fewer terms, I don't know, but I know I don't need any more. So how would I ever do that? That looks a bit complicated. So, well, because I have to use these higher powers of, these powers of radical minus 3 plus radical 7, I want to see which of them will actually be useful for me to write radical 7. So first I try the square. If I square that, I already know what I get because we just did this calculation. I get minus 3 plus 7, so 4, plus 2, radical minus 21. Now, note, this does not look that useful for expressing radical 7 because on the right hand side I didn't even get radical 7. So let's try another power. Let's try cube. So I'm going to use the formula for the sum, for the cube of a sum. That's the first term cubed plus 3 times the first term squared times the second term plus 3 times the first term times the second term squared plus the second term cubed. All right, that's quite a mess. Let's see what we can get from this mess. So this is radical minus 3 to the power 3. So that's the same as radical minus 3 to the power 2 times radical minus 3. And radical minus 3 to the power 2 is just minus 3. So that's just minus 3 radical minus 3. Plus, okay, again, this thing here is just minus 3. So that term here is just minus 9 radical 7. Plus, okay, well, radical 7 squared is just 7 times 3 is 21. And this is going to be 7 radical 7. Okay, well, at least I got some radical 7 on the right hand side. Let's see exactly how many. So I get, these two give me 18. And these two give me minus 2. So I've got 18 radicals minus 3 minus 2 radical 7. Oh, okay, well, you know, you may be now becoming more well versed in these tricks. So now look, if I subtract from this 18 times this, which is minus 18 radical minus 3 minus 18 radical 7, all together, this gives me just minus 20 radical 7. So I didn't quite get radical 7, I got minus 20 radical 7, but rational in front of it is not a problem. So as a conclusion, I got from this calculation, radical 7 is, okay, so minus 20 radical 7 is, so let's just write minus 20 radical 7 first. So minus 20 radical 7 is minus 18 plus this. Okay, have I done this then, what I wanted to do? Yeah, I mean, I just need to now divide by negative 20 to get, that's 18 over 20 plus negative 1 over 20. Okay, it's kind of interesting that radical 7 is equal to something like that. Look, right, so now that means I got a0 to be 0, a1 to be this, a2 to be 0, and a3 to be this. So this proves that radical 7 is in that field. So I get that radical 7 is actually in this field. But if radical 7 is in this field, then Q adjoint radical 7 is a subfield of this field. So in that case, that means I can write here an intermediate field, Q adjoint radical 7 in between those two fields. And now I gain some knowledge, because now I know this degree is 2, right? Because the minimal polynomial of radical 7 over Q has degree 2. So what is this? Let's think about that. So by the Dedekind product theorem, I get that 2e is equal to d. And I know that d is at most 4. That's what we already proved. So what are the options for e to be? E could be 1. E could be 2. And that's it, right? Anything larger than 2 would give me d bigger than 4. So if e was 1, then these two fields would be the same. Oh, but if these two fields are the same, that means this number lies in that field. Okay, you may pause the video now if you wish and try to think about why this cannot be true. So this cannot be true because this is completely contained inside the real numbers, right? It's a rational plus rational times radical 7. And this is not real. So contradiction. So E is 2. Hence D is 4. Okay, so we've got that the degree of the extension here is 4. And remember, so recall that the degree of any field adjoint an algebraic element is equal to the degree of the minimal polynomial. When we started talking about degrees of extensions of fields f adjoint alpha, we were using this sort of equality, but in the other direction. We found the minimal polynomial, and therefore we were able to say what the degree here is. Look, now I'm using this equality in the opposite direction, namely I computed this to be 4. Therefore, I conclude that the degree of the minimal polynomial must be 4. So this this is 4. So this, which was a polynomial of degree 4, must be the minimal polynomial.